Alright, now it's talking about empirical formula, and if you have percent composition, which we talked about in an earlier video, then you can also find empirical formula from that. Because remember what percent composition is. It says what percent by mass. So if you know that you have a compound that is 5%, let's say 5% hydrogen, let's say, then for every 100 grams of the compound, that equals 5 grams of hydrogen. That's what the word percent means, per 100. Doesn't that look like a conversion factor? Yes, it does. So we can use it as a conversion factor. And that's precisely what you do with percent composition. We're not going to spend very much time on this. You either get empirical formulas or you don't, pretty much. No matter how much time we spend on them, students can seem to struggle. Notice what it says. This is in your textbook, by the way, on page 94, I believe it is, where it says, to determine the empirical formula of a compound, it tells you that's 30.45% nitrogen and 69.55% oxygen by mass. Percent means per 100, so we are going to assume 100 grams. That's why you do it, because it says percent. And you know that if you have 100 pennies, that's assuming percent, okay? 100, the word means. So if you had 100 grams, you would have 30.45 grams of nitrogen and 69.55 grams of oxygen. That's exactly what you do. Then you're going to take each one of those and change those grams into moles. How do you change grams into moles? Well, we just spent a good 40 minutes learning how to do that. How do you change grams of nitrogen to moles of nitrogen? Okay. I'm not the hugest fan of exactly how Dr. Burge here does it, but that's okay. This is her setup of it. I prefer the given and the unknown, but this is exactly what I would do. I would show my given, though, and I would show my unknown. Here's my given. Here's my given right here. There's my nitrogen. Here's my given for my oxygen. And then my conversion factor is going to be for every 1 mole of nitrogen, I have so many grams of nitrogen. Where do I fill in that blank right there? Right here? I fill it in from the chart. And if you'll look up on the chart for nitrogen, you're going to see it says 14.01 grams. That's where that 14.01 came from. So this is how many moles of nitrogen you have. And that is how many moles of oxygen you have. All right? Well, you know that you cannot, according to Dalton's law and his kinetic theory, you cannot have a piece of a mole. You can't do that. So what you do here, just like with any ratio, you're going to choose the smallest number. And that's easy enough to do. Which one of these two numbers is smaller? 2.173. And you're going to divide both of these numbers by 2.173. As if you would in any math find the smallest of the two numbers. We're looking for the smallest mole ratio, and to do that you're going to find the smallest and divide both of those by it. So when we divide that, 2.173 divided by 2.173 is 1. So there's 1 mole of nitrogen for every, now 4.347, when I take 4.347, you hear me get my calculator, 4.347 347 divided by 2.173 is 2.00046. And that is close enough, for sure, to round it to 2. Now, so the mole-to-mole ratio of nitrogen to oxygen is for every 1 mole of nitrogen, there are 2 moles of oxygen. So my empirical formula, or the lowest whole number ratio of nitrogen to oxygen, is 1 to 2. That's my formula right here. Now, the kicker is that your mole-to-mole ratios have to be extremely close. If this had turned out to be 2.2 when you divided, you could not round that down. They have to be very close to whole numbers to be able to round them off. If they're not, then you have to come up with a number to multiply through by, like in fractions, until you get whole numbers. Okay? And then it shows you another example here, right here. Suppose that in an experiment of the combustion of glucose, it gives you this breakdown of what's produced. 18.8 grams of glucose produced 27.6 grams of carbon dioxide and 11.3 grams of water. So how would you do that? You also know that in order for this combustion to take place, what else had to be present? Oxygen. In every single combustion reaction, oxygen must also be present. So you know that had to be true. So we can calculate the mass of carbon and hydrogen in that original sample of glucose, and it shows you exactly how to do that. Okay. Here's our sample of carbon dioxide. It shows you there's your sample of carbon dioxide. The carbon in it, oh, I didn't mean to do that. There's your sample of carbon, and there's your sample of hydrogen. And it changed each one into moles. It used the molar mass to change each one into how many moles is that. Okay? And so you can see how many grams of carbon you had and how many grams of hydrogen you had. All right? And then you can find out how many grams of oxygen you had. Now, I didn't spend very much time on this because this is not something that you would normally do in Chem 1. This is for sure more of a Chem 2 type problem. But finding empirical formula from percent composition is for sure a Chem 1 problem. And you will have to do that. Okay? But you can see again, they took the mass of each one, they changed it into moles, and the moles did not turn out even, 0.67627. You can't have a piece of a carbon atom like that. So what did they do? They chose the smallest one and they multiplied through. Okay? And so now we have the empirical formula is going to be 1 carbon, 2 hydrogens, and 1 oxygen. That's the empirical formula. Alright, but what I wanted to get to is this. Once you have this empirical formula, once you've done all that work and you found the empirical formula, how can you find the molecular formula from it? This is actually quite easy, and I will expect you to do this. Once you have the empirical formula and you know the molecular formula, here's the molecular molar mass right here, you can find the actual molecular formula for, say, glucose in this case. What you do is you're going to find the molar mass of our empirical formula. So let's take our empirical formula that we found, our C1H2O1, and let's find its molar mass. Well, carbon, that's 12.01. Hydrogen, we have 2 of them, remember, and each one is 1.01, so that's 2.02. And then oxygen, remember, is 16. So that's 12 plus 2 is 14 plus 16 is 30. 30.03, which is close enough to 30, I think. And then it tells us that the molar mass for glucose is 180. So what you're going to do is you're going to take 180, the known molar mass of glucose, and we're going to divide it by the molar mass that we found, 30, and you get 6. Well, what do we do with that 6? You're going to take this 6 and you're going to multiply each one of those by 6 to give us the actual molecular formula for glucose. Okay? Let me give you a math example of what we're doing. It's like you had a 6 on the outside, and you had 2x plus, well, let me back up. Let's say that we had x plus 2y plus z. Okay? And we need to find out when we distribute this 6. Okay? We're going to end up with 6x plus 12y plus z. That's exactly what we're doing. We're going to take this 6 and we're going to multiply it times this c. It has a little subscript of 1, so it's going to be c6. That h has a subscript of 2. 2 times 6 is 12. h 12. And then this o has a subscript of 1, so we're going to multiply it. So this is our actual formula. Okay? So we're going backwards. Earlier in chapter 1, I think it was, when we were talking about empirical formulas, we said, what can we divide all of those numbers by? We can divide all of those numbers by 6. So we divided them out. Now then, we're multiplying it back to find the actual formula. Okay? Now, finding empirical formula is hard. But once you find empirical formula, then finding the actual molecular formula is very, very easy. And then it gives you another sample problem. This is sample problem 3.9 in your textbook on page 96. And it's just working you through another example of this process of being able to find the molecular formula when you're given or when you find empirical formula. Okay, this is, you found the empirical formula first, and then you're going to find the molecular formula.